Exoplanets are planets that are orbiting other stars outside our solar system, and we're interested in them because we're interested in knowing how our system formed, and also is there life around other stars in our galaxy. My name is Sandrine Thomas. I'm an optical scientist at the University of California, Santa Cruz, and I work here at NASA Ames Research Center. Nowadays, we find exoplanets with different methods, mostly indirect. So the first one is the radial velocity technique. It actually measures wobbles of the actual star. So when a planet goes around a star, the gravity between the two bodies actually makes the star itself wobble. The second technique is microlensing, so using the fact that a star can actually act like a lens and then kind of image the background star through that other star. And then we have a very popular technique right now, which is the transit technique. And it actually looks at the planet going in front and behind the star, and that will affect the light coming towards us. The methods used so far, transit, microlensing, radial velocity methods, they actually do not allow us to define the atmosphere of a planet or the composition of a planet. The only information we have are the masses or the size of the planet. To overcome the limitation of these techniques, we have this last method, which is a direct imaging. And that's what we're going to use to actually take spectra and understand more about the composition of the planets. The main challenges that we have with direct imaging are, one, we need to image a very faint object next to a very bright object. To give an analogy, it's like looking at a firefly next to a lighthouse in California from Hawaii. And the second one is, in order to make sure we can actually see it, even if we had the contrast necessary to see the planet, if it's distorted or if there's vibration in the system, we will not be able to see it. We will just see a big blob. These challenges are overcome by using a chronograph that will remove the light coming from the parent star. And then the second one, to overcome the wavefront aberration and the distortions, we use what we call a deformable mirror. And that deformable mirror actually changes in real time to compensate for the turbulence and the vibration in the system. One issue we have with chronograph nowadays, the ones that have been used so far, is that in order to block the light coming from the star, we're putting a big mask. So that means that if you block the star, we also block what's around the star. So if a planet is really close to the star, we will not be able to see it. This specific type of chronograph, the PIAA, what we call, is enabling us to actually look really close to the star. So we actually are able to decrease the area that we're going to block from the star, so then we actually can see planets really close by. We have a testbed here at NASA Ames where we have a PIAA and we also have a deformable mirror, and we're putting all that together to get the highest contrast that we can. And my role in here is to make sure we do by, one, making sure the testbed, our setup, is really stable. We isolate all the vibration or the ghost that can actually make the image worse. And then my second step is to do wavefront control. So that means what I'm doing, my goal is to get a really dark hole region. And by doing that, I'm actually changing the mirrors to send the light away from that region that I want dark to be able to detect the planet. What really fascinates me about this work is many things. One is the fact that I really like stars and I really wanted to understand them. And that is in the fact that I really liked math. And so I was really good at math when I was a kid, and I just wanted to apply that. And I slowly went from astronomy into looking at planets, because for me that was a very first interesting math problem and optical problem, and also trying to find planets somewhere else and trying to see if our solar system is unique or not is really fascinating. If a student comes to me and asks me about pursuing a career in astronomy or at NASA, I would tell them two things. One, to be motivated, and two, to have a very specific goal, so know what you want to do, like either professorship or faculty position or engineering. So in my case, I chose to do an optical engineering degree. And the second thing is make sure you actually learn math and science.